Greetings all, welcome back. Now I want to talk about something slightly different with regard to these particular two differential equations. I mentioned last video, that I'm comparing these two first order linear differential equations because they have a bit of structure in them that while they look relatively similar, they're actually quite different. Okay, and last time I talked about what was the general solution to a differential equation, an expression encompassing all of the solutions of a differential equation. Now today I want to talk about something a little bit more particular, excuse the pun. I want to talk about a particular solution. So back to the generic here. Y of x equals x squared over 2 minus 2e to the x over 2 plus c is the general solution to A. Because remember, we're dealing with this guy now. We're solving this one, right? So if I take the derivative of this and I stick it into here, I will get the right-hand side. And as another definition, a particular solution to a first order ODE is really just a choice of the unknown constant. Okay? Now, how do we do that? One, we can just choose the value of c and we have one of our solutions. Two, sometimes in the differential equation, they denote, or there's some extra information lying around that gives us a sense, right? So possibly if we knew, for example, that y of 0 equaled 1, so if we were given this differential equation, dy dx equals x minus e to the x over 2, and we were also given a bit of information, like I know that the solution I'm looking for at time 0, so okay, at x equals 0, it's 1, then these two things together tell me that I don't need to worry about the c. Once I find the general solution, I can solve for the c, and then I actually have a solution to my differential equation. Here, this piece of data, y of 0 equals 1, is called an initial value. And that initial value might be, hey, when I start my experiment, because this is a mathematical model, right? I'm trying to study something new. I know that a particular value of the independent variable, I know that the dependent variable takes something. If it takes a value, then I know that that's the solution I want. So if I solve my differential equation, I get this generic set family, one parameter family of solutions. If instead I knew one bit of data, then I have, if I knew an initial value, then I can solve for the particular solution, particular function. Here, in the ODE, with its initial value, we have a name for that actually because it shows up so much in differential equations. It's called an initial value problem. Because I guess all the really more interesting names were taken. And we just tend to call it an IVP. So if we're looking for something like an ordinary differential equation, if we're just given the ordinary differential equation, we call it an ODE. If we're given also an initial bit of data that tells us which particular solution we're looking for, then we call that thing an initial value problem. So this thing together with this would be an initial value problem. Okay, so just to take this one step further, I mentioned this the last time, but I'll mention it again. Y of x equals x squared over 2 minus 2 e to the x over 2 plus 3 solves the IVP. Y prime equals x minus e to the x over 2, y0 equals 1. That is an initial value problem because it's an ordinary differential equation with an initial value. By the way, the initial value does not have to be t or whatever, x in this particular case equal to 0. It's any starting point. So if I want to start my experiment at x equals 42,000, and y at 42,000 was 6, that's my initial value, even though t is not 0 there. There's going to be many differential equations where they're not defined, the function isn't defined at 0. So we can't really just call that the initial value. It's whatever we'd like it to be. The value of the independent variable can be whatever it likes. If we're given a bit of initial data here, then this entire thing is called an initial value problem. Okay? So we can actually solve with a particular solution. Anyway, that's all for now. Thank you for listening, and we will talk again very, very soon.